Hello all, this is the Pencrest High School AP Physics C video series. This is video 2C, velocity dependent forces. So we've spent a year plus ignoring wind resistance and air friction and all that. What we're going to do now is look at quantifying it. We're going to see how it works. What we find is that air and other fluids provide a friction force that acts in a similar fashion to surface friction in that the force opposes the motion. This force, which is usually called F sub d or a drag force, depends directly on the velocity of the object. It tends to increase in magnitude as the velocity increases. There are a couple of possibilities in terms of the functionality of this force. We could see a linear dependence on velocity where F sub d equals negative BV. You see this frequently in liquids, water, oil, things like that. In terms of air resistance, quadratic dependence is a little more realistic. In this case, the drag force F sub d equals negative BV squared. All gases tend to display this kind of functionality. In both cases here, what you see as a B term is a constant that depends on several factors, including air density, humidity, temperature, cross-sectional area, the shape of the object, how rough the surface is. There's a whole bunch of them. We might refer to it in either case as a drag constant. The term could be any symbol at all. Certainly on the AP exam, they've used K, they've used B, they've used C. They could use any conceivable symbol for this thing we call a drag constant. I want you to note that the units in each case for the drag constant would be different depending on the functionality of the force and the velocity. In each case, we would need the entire term on the right side to have units of force because, of course, each expression is for a drag force. Recall that force has units of kilogram meter per second squared in fundamental physics units. So you may need to manipulate the quantity B to figure out what its units would be. Going a little deeper into this, in fluid mechanics, when we have a quadratic dependence of force on velocity, we see that the magnitude of this drag force is 1/2 C rho A V squared. C is a drag coefficient. Rho is the fluid density in kilograms per meter cubed. Capital A is a cross-sectional area of the object as it moves through the fluid. When the AP exam uses a drag constant that we called B earlier, it's effectively all of these factors combined into a single constant expression. The C term here, what they call the drag coefficient, is dimensionless and depends only on the shape of the object that's moving through the fluid. So we're not going to go this far, but this is how it's presented in Halliday-Resnick and any introductory fluid mechanics course that you could take later on. Now, when an object is in free fall through the air or any other fluid for that matter, the drag force on the object increases in magnitude as the velocity increases until such time that the drag force is equal to the weight of the object. So with something in free fall, the weight of the object pulls down, the drag force pulls up. and the drag force increases until they are equal. At this time, the acceleration becomes zero because the net force is zero, and the object has reached what is called terminal velocity. Terminal velocity is indicated with v sub t. The key thing to recall here is that at v sub t, when the object is at a terminal velocity, its acceleration is zero. So technically it's no longer in free fall, because free fall is defined as something that is subject to only gravity. But I guess when you jump out of a plane, you start at free fall. Now we would see that the force equation that governs this motion looks like this: mg down minus fd equals ma. Again, the object is typically moving down, so that mg term, that weight force pulling down, would tend to be positive. The drag force due to the air resistance would be up, and the sum of the forces would equal ma. Now, this is called a differential equation because it has both acceleration and velocity in it. Recall that F sub d, the drag force, depends on velocity. So velocity, we already know velocity is the first derivative of position with respect to time. Acceleration is the second derivative of position with respect to time. They're both in the same equation. That's what makes this a differential equation. If we were to take this force equation and in each case replace the drag force with its functionality with v, so for example mg minus bv equals ma, and then we replace the a with dv dt. This now has been written as a differential equation in terms of the velocity v. So we have velocity in here, and we also have dv dt, or the first derivative of velocity. Similarly, we could write it down here for a drag force that has a quadratic dependence. Let's not worry too much about these here on the right. But frequently, what's going to happen is the AP exam will ask you to write a differential equation that governs this sort of behavior. And what they really mean is write a force equation and replace the acceleration with dv dt, which effectively makes a force equation into a differential equation. They will frequently say, write but do not solve this differential equation. So ultimately, we're going to see how to solve this equation for v of t, v as a function of t, but not just yet. So that's going to come a little bit later when we get a little closer to the AP exam. Now, as this object falls from rest, say you're jumping out of an airplane, its acceleration is initially the acceleration due to gravity downward. The acceleration will gradually decrease as the drag force increases. Mg stays the same, but the drag force will increase until the forces cancel and the object reaches terminal velocity. So if we consider what the velocity and acceleration graphs would look like, we can see that the velocity is increasing. In both cases, down is positive here. The velocity increases, but at a decreasing rate, because the magnitude of the acceleration is decreasing as the drag force increases. The net force on the object will follow the acceleration, or determine the acceleration. So as the net force, as the drag force increases and approaches mg, the net force will approach zero, and so will the acceleration. So you can see here that when the object reaches terminal velocity, the acceleration goes to zero, and the velocity curve will level off. The value of the velocity at this level here, where it levels off, where it flattens out, the value of the velocity at this point is the terminal velocity v sub t. Okay. So that's going to wrap it up for velocity-dependent forces. We're going to do, we do have a weekly WebAssign associated with this, but it's relatively small. And we also have a nice experiment coffee filter lab that goes with this. So I guess that's it. Until next time, thanks, and we'll see you again soon.